Hey guys, this video is going to be Introduction to Covalent Bonding, Lewis Structures, and Formal Charge. Alright, so what is it and why do we care? So the simplest definition of a covalent bond is when two atoms of similar electronegativity shares a pair of electrons in order to complete its octet. Usually they're nonmetals. So before we get into it, electronegativity is an atom's property that allows it to pull electrons from other atoms towards itself. So we don't talk about an atom having high electronegativity if it pulls its own electrons towards itself. So if it has a high electron affinity, that's what we call it. Electronegativity, it goes outside of itself and pulls electrons from another atom towards itself. So elements that have a high electron affinity or high ionization energy also have a high electronegativity, but that's why we have two different words for it. So whenever you're talking about electrons being pulled towards another atom across a bond, that is electronegativity. So high electronegativity is going to be up in the top right corner of the periodic table, not the noble gases. So these are elements that have high electronegativity, and that's why we say that it's usually nonmetals. So if fluorine and oxygen bond together, then this bond would have two electrons in it, and the electron density of that bond would be pulled towards fluorine slightly because it's more electronegative than oxygen, and oxygen doesn't have the electronegativity to be able to pull back. But they would still share these electrons, it just wouldn't be even. And so if you look down here, that's what we call a polar covalent bond. So we've got chlorine and carbon, and they're sharing these two electrons. And so, but they're closer to chlorine because chlorine's more electronegative. And so this side is slightly negative while we leave carbon slightly positive. Another type of covalent bond is a nonpolar covalent bond. So hydrogen, both hydrogens have, this table says 2.2, I've always seen 2.1, but they have the same electronegativity. So if they have the same electronegativity, then they're going to share these electrons equally, and neither one can pull the electrons towards itself, or the electron density rather, towards itself. So they share them completely equally, and so that's nonpolar covalent bond. And then an ionic bond takes a polar covalent bond and takes it a step further. So if we look at sodium, sodium's electronegativity is 1.01, and chlorine's electronegativity is 2.83. So these two electronegativities are very different from each other. And because chlorine is so much more electronegative than sodium, it doesn't just pull the electrons towards itself, it takes it. And so we end up with an ionic bond because there's two ions being attracted to each other by now electrostatic charges because one is negative and one is positive. So let's look at a covalent bond in more detail. This is a potential energy curve showing the potential energy versus internuclear distance. So along the x-axis we have internuclear distance. And what that means is that is the distance from nucleus to nucleus between two atoms. And so this is for hydrogen. And up here at the top, what we would basically have is two hydrogen atoms overlapping each other. And so they have repulsive forces up here because they're too close together, they can't form a bond. So the two nuclei of the hydrogen atoms are too close together and pushing away from each other. And then once we get down here to the minimum, this is when the most stable bond will occur because they're at the right distance from each other to share those electrons perfectly. And it's always going to be at the most negative value in energy. That's the most stable value. And then they'll keep moving further and further apart, but there's going to be an attractive force that's going to kind of pull them together. And then eventually it gets to the point to where no bond can occur because they're too far from each other. So there won't be any attractive forces anymore. So the most stable state will always be at the bottom. Now, if we were to compare a curve for oxygen or nitrogen gas, so we have oxygen would look like this if we were to draw the Lewis structure, and then we have nitrogen. So this is a double bond, and down here is a triple bond. And double bonds are shorter in length. A single bond is going to be the longest. Double bond is shorter, and then a triple bond is even shorter. So the length of the bond is shorter for nitrogen to nitrogen, but the strength of the bond is also higher. So the strength is going to be the opposite. So a triple bond has more strength than a double bond, and then a single bond. So that means it's going to have higher energy. Triple bond would be, the minimum would be further down here, and it would also have more energy, so it would dip down further. Okay, and then a double bond would be between these two. So it would look something like that, maybe for nitrogen, where it's going to have a shorter minimum, right? A shorter minimum, so for nitrogen, and it's going to be stronger, so it would require more energy to break. So you have to put energy in to break bonds. Just like if you were going to break a pencil, if it's a shorter pencil, you'd have to put more energy in to break it. And you're going to get energy out when the bond is made. And it's going to be the same amount of energy required to break it, just in opposite in sign. There we go. Okay. So let's look at some Lewis structures. All right, so covalent molecules contain a covalent bond. We also just call them molecules. If it's called a molecule, that means it has covalent bonds. And unlike ionic compounds, covalent molecules do not have set ratios they exist in. So carbon can bond with oxygen as CO2, and it can also bond as CO. So you can't just say, oh, magnesium is going to be +2 and chlorine is going to be -1, so it'd be MgCl2. It can only exist in that ratio. Whereas carbon, if we were to use charges here, even though this is not correct, carbon could be 4+, oxygen could be 2-, and so we would only get CO2. But that's not what we see. We also know that carbon monoxide is a real thing. So they're not using charges here to get these. It's just completing each other's octet, and how many different ways can you put those two things together? All right, so we can use a method of counting the electrons like we used last year. Okay, so if we count the total number of valence electrons, the element listed first goes in the middle, unless it's hydrogen, because hydrogen can only make one bond, so you can't see hydrogen do this thing. That doesn't work. It can only make one bond because it only has the 1s orbital, and that's it. After that 1s orbital holds 2 electrons, it's completely full, and it doesn't have a second energy level to be able to hold any more electrons, so it can't do that. We're going to bond all remaining elements to the central atom. Each bond is made from 2 electrons. Distribute the remaining electrons to outer atoms. If any electrons remain, we put them on the central atom. So if we have any electrons left over, we're going to put them on the central atom. It doesn't matter if it already has 8 electrons around it. We're going to still put them on the central atom. And then we're going to check the octet rule for all atoms. If an element does not have the octet rule satisfied, we use double and triple bonds. What that means is that you only make double and triple bonds when you don't have enough electrons. You don't make double and triple bonds when you have too many. So if you don't have enough, we're going to use double and triple bonds. All right, and then don't forget about resonance, and I'll talk about that while I do these. So my first example is SO3, and sulfur has 6 valence electrons. Oxygen also has 6 valence electrons, but we're going to multiply that by 3 because there are 3 oxygens. So that would be 24 valence electrons total. I'm going to put sulfur in the middle and bond my oxygens to it. And I've got 2, 4, 6 electrons out there already because there's 2 electrons in each bond. 8, 10, 12, 14, 16, 18, 20, 22, 24. So that's 24 electrons, and I don't have any more electrons to put out there. I'm completely out. So then check my octet rule. Now, oxygen has 8, but sulfur only has 6. So one of these oxygens is going to have to share more. So I'm going to take one and put it there. Now, did I have to pick that oxygen? No, I didn't. I could have drawn it like this. and that would have been okay too. Those are equivalent resonance structures. So this sulfur trioxide would have 3 equivalent structures. That would be resonance. So what we see in resonance and why it is important is we just talked about how a single bond is longer than a double bond. Well, in sulfur trioxide, what we see is that all 3 of those bond lengths are actually the same length. So if there was really only one double bond here, one bond would be shorter than the other, but that's not what we see. And the bond length, though, is actually between a double bond and a single bond length. So it's longer than a double bond, but shorter than a single bond. So that tells us that all 3 of these are coexisting at the same time. And when we look at formal charge, we'll see actually what's happening here, but it's really because of resonance. And so this would have 1/3 double bond character and 2/3 single bond character. And that would be a good explanation for what we see in SO3. All right, so what about H2CO? All right, so hydrogen has 1 valence electron, and there's 2 of them, so that means I've got 2 valence electrons. Carbon has 4. Oxygen has 6. So that would be 12 valence electrons total. Now I can't put hydrogen in the middle because it only has that 1s orbital, but I can put carbon. That's 6 valence electrons. 8, 10, 12. I went to the outer atoms first. Now I'm going to check my octet. Hydrogen it's good because it can only have 2. That is actually its octet. It wouldn't be an octet though. It would only be a ditet, I guess. And this hydrogen at the bottom is good. Oxygen is good, but carbon needs 2 more electrons. It only has 6 around it. So I'm going to take a pair from this oxygen and make a double bond. Now there would be no resonance here in this structure, so this would just be it because it can't make a double bond with the hydrogen. All right, ClO2 negative or chlorite. So we have chlorine has 7 valence electrons, oxygen has 6 times 2 equals 12. And then we have +1 because it has a negative charge, so that means it has an extra electron. So this would be 20 electrons total. We're going to put a oxygen or chlorine in the middle, oxygen on the outside. So right now that's 16 electrons. Now I have 20, so I'm going to put 2 more here and 2 more there. And put brackets around it to show the charge. So everybody's octet here is complete, and this would be a good structure if we're just following the octet rule. All right, so we're going to do a few more examples. These are a little bit different because they're more organic molecules, and so I want you to see what happens when we have it drawn out like this. So this first one, we have C2H4. And so carbon has 4 valence electrons times 2 would be 8. Hydrogen, 1 times 4 would be 4. And so all together, that is 12. And so I'm going to put my carbons here in the middle. And then I'm going to put 2 hydrogens on this side and 2 hydrogens on this side. So right now, that's 10 electrons. And each carbon needs another 2. So I could pick one of these carbons to be my outer atom and one to be my central atom. And if I did that, then I would put a pair of electrons on one of them, which then shows that these electrons have to come down here and double bond. So you can do it that way. Some people can just see it. It really doesn't matter. You can just pick one of the carbons to be your central atom if you need that. And so that would be the Lewis structure for C2H4. CH2NH. So let's see. The way that this is written is telling you the order of the atoms. It's saying that we have a carbon with 2 hydrogens connected to it, that's connected to a nitrogen, that's connected to a hydrogen. So if I was to count up the valence electrons for this, I would have 3 for hydrogen, and then I would have 4 for carbon, and then I would have 5 for nitrogen. And so that would be 12. So right now I've got 2, 4, 6, 8 electrons, and there would be 10 between carbon and nitrogen and 12. With some of these, it's easier to look at the bonding patterns. I don't think that they'll make you draw one of these on the test, but I've seen them use these molecules, and so if you've seen them more often, it makes it less confusing. But you could have gone ahead and said, okay, carbon's my central atom, so I'm going to put 2 electron pairs, the remaining electrons, on nitrogen, because nitrogen would be your outer atom, and then it would be very obvious that one of these pairs would have to come down here and share with carbon. And so now nitrogen has 2, 4 from the double bond, and then 6, the lone pair, 8 with the bond between nitrogen and hydrogen. So everything has its octet complete there. C2H2. Carbon has 4 valence electrons. Hydrogen has 1. So this would be 10 valence electrons total. So again, I'm going to put carbon, carbon. So there's 6 electrons. I have 4 more. So there's 2, 4. And then these will come down here, and a triple bond will form. Now everybody's octet is complete, and that is a good structure. All right, CH3, CCCH3. So remember, when you have a pattern like this, it's telling you the order of the atoms. All right, so first I'm going to count out my valence electrons. So I have 4 carbons, and each one has 4 valence electrons, so that's 16 for carbon. And then hydrogen has 1 valence electron, and there's 6 hydrogen. So that's 6 valence electrons. So that's 22 electrons total. And I'm going to go ahead and write it over here so I can refer to it. So this is the very first part. So carbon has 3 hydrogens, and then it's attached to a carbon, that's attached to a carbon, that's attached to a carbon. Oh, I made too many. That has 3 hydrogens attached to it. All right, so right now I've got 2, 4, 6, 8, 10, 12, 14, 16, 18. So that means that I have 4 more electrons to give out, or 2 more electron pairs. So I'm going to put those 2 electron pairs here. And this carbon doesn't have enough, so these electrons will come down here and share extra. So now everybody has the octet complete, and this would be the structure for that. All right, and then the last one we have is CH3COOH. And this is acetic acid. It should look familiar to you. So CH3COOH, carbon has 4 valence electrons, and there's 2 of them. Hydrogen has 1, and there's 4 of them. And then oxygen has 6, and there's 2. So that's 12 plus 4 plus 8. So that would be 24 valence electrons. And it says that we have a CH3 bonded to a carbon that has 2 oxygens attached to it, and then a hydrogen. So this would be 2, 4, 6, 8 around the first carbon, 10, 12 for the double bond, 14 between carbon and oxygen, and 16 between oxygen and hydrogen. So that means that I've got 8 valence electrons left, and all my carbons look good. Hydrogen is fine, but the oxygen here needs 2 more pairs of electrons, and the oxygen here needs 2 more pairs of electrons. And so that is all 8. And so that's what the structure would look like. And anytime you see the COOH, that's an acid, and that right there will always be attached to an oxygen, and then this oxygen will have the double bond. So one will be double bonded to carbon, and the other oxygen will be single bonded to carbon. So that is the COOH part of that structure, always, in every compound. All right, so some elements can exceed the octet rule, and we've seen this sometimes, but sulfur does it a lot, phosphorus do this a lot, and the halogens, chlorine, bromine, and iodine do this. They have to be below the 3rd period, and this is simply because in the 3rd period is where the first D block occurs. And so even though sulfur ends with 3s2, 3p4 and has no d electrons, that d block is still present. And so they can put extra electrons inside of the d orbitals and hold them there and make bonding patterns with them. And so that's why it has to be in the third period or lower, because there's a 3D and a 4D and a 5D, but there is no 2D. So elements in the second period can't do this. So nitrogen, oxygen, fluorine, they can't go past the octet rule. Let's look at some examples. So like SF6 is an example of exceeding the octet rule. So we have sulfur, and that would be 42 plus 6 is 48 electrons. So every single one of these fluorine has 6 lone pairs. We also call those non-bonding electrons. All right, and then there's also like PCl5, BRF3, I think exceeds the octet rule. All right, so formal charge. Formal charge is a way to be able to determine which structure will be the most likely structure. It also kind of keeps track of where the electrons are in the molecule. You can either take the group number and subtract the non-bonding electrons and half of the shared electrons. So these are the bonded electrons, the electrons in the bond. And the non-bonding electrons would be the lone pairs. Or, this is how I do it, we take the number of valence electrons that the atom typically has by itself, and then we assign a certain amount of electrons towards it. So if I'm just going to look at this, and we'll just say that this is the simplest one first, okay? Then carbon usually has 4 valence electrons. And if they're really sharing these electrons, which they are, it's a covalent bond, then we're just going to assign one of the electrons to carbon and one of the electrons to hydrogen. So carbon would have 4 electrons assigned to it. So it's always going to be half of a bond. And so that would be -4. So the formal charge here on carbon would be 0. It wouldn't have a formal charge. So let's look at some that do. All right, so oxygen has 6 valence electrons, and hydrogen has 1 valence electron, times 3. And then we have a plus charge. So we're going to subtract 1, because if it has a positive charge, that means you subtracted an electron. So we're going to have 8 valence electrons. So oxygen will be in the middle. We put hydrogen on the outside, so that's 6. And then there's 8. All right, so now looking at my formal charge, oxygen should have 6. But when we look at it, right now, we're going to take 1 electron from here and assign it to oxygen. So that would be 3 electrons from the bonds. And then the 2 electrons that are obviously assigned to oxygen are those 2. So that would be 5. So that means that the +1 charge is on the oxygen. So the formal charge of oxygen in hydronium is +1. And that's where this +1 charge is. So the sum of all the formal charges in the molecule should give you a +1. So if we're going to look at the formal charge of hydrogen in here, hydrogen should have 1 electron, and it does, because we're taking the other half of that bond and assigning it to hydrogen. So it's a covalent bond. We know they're sharing those electrons, even if it's not equally, and we're going to split that bond in 2 and assign half of it to one of the atoms and the other half of it to the other atom. All right, so let's look at nitrogen monoxide ion here. So nitrogen has 5, plus the oxygen has 6, and we're going to subtract 1 from the positive charge. So that would be 10. So we have nitrogen, oxygen, so there's 2, 4, 6, 8, 10. Now this nitrogen is obviously lacking, so I'm going to move those electrons over here and make a triple bond. So now looking at this, nitrogen should have 5 valence electrons, and it does. If we look at it, we have 1, 2. Those lone pairs are assigned to nitrogen. 3, 4, 5. So -5 is 0, so the formal charge on that nitrogen is 0. And then oxygen, we have 1, 2, 3, 4, 5. Oxygen should have 6. -5 is going to be +1. So the +1 charge is on oxygen. All right, so let's look at this. We've got nitrogen and then boron. Okay, and we want to know what has formal charge and where. So hydrogen is good. You don't have to compute the hydrogens, but hydrogens, all of them would be 0 because it should have one bond. If it has one bond, it's 0. It's always going to be 0 for hydrogen. Okay, now nitrogen should have 5, but right here in this molecule, it has got 4 because there's 1, 2, 3, 4 assigned to it. So this nitrogen would be +1. Now boron should have 3, but it has 4. It's got 1, 2, 3, 4. So the boron is going to be -1. So now if I draw structures for SO3, we already drew it once. We drew this. And if I'm going to assign formal charges to it, the oxygen should have 6. But here we've got 1, 2, 3, 4, 5, 6, and then half the bond, 7. Same thing would be happening with this oxygen on the bottom. We have 1, 2, 3, 4, 5, 6, 7. And then the oxygen on the right with the double bond, we should have 6, and we've got 1, 2, 3, 4, 5, 6. And then sulfur should have 6, and we've got 1, 2, 3, 4. So we know that the total charge here is 0 on this molecule, and that's what we see. We see +2, -1, -1. That comes out to 0. And so that is a good molecule. And it is acceptable. But sulfur is one of the elements that can exceed the octet rule and does a lot. So what does this mean? When we look at a structure and we want to determine which structure is better, we're looking to see one that minimizes formal charges. And I'm going to talk about this again in a little bit, but one that minimizes formal charge. And what that means is make more of them zeros. And if we can't minimize the formal charge, we want to put the formal charge on the most electronegative element. Now, if I was to Google the Lewis structure for SO3, this is what I would see. Is that an acceptable structure? Yes, it is, because sulfur can exceed the octet rule. And when we look at formal charges, if I was to compute the formal charge on the oxygen, it should have 6, and it's got 1, 2, 3, 4, 5, 6. So that's 0. And if I was to look at sulfur, it should have 6. And so there's 1, 2, 3, 4, 5, 6. Now you don't have to come up with these on your own, usually. Usually when it comes to formal charge, they'll give you a choice. And they'll say which one would be better. Or they'll draw a skeleton structure and have you put in bonds and electrons. And they'll have the single bonds in already. So it's a little easier to see when it's like that. But you should be able to determine that this one would be a better structure so long as sulfur is the one exceeding the octet rule and not oxygen, because oxygen can't do that. It has to be an element in the third period or lower. All right, H2CnH2. So we've got carbon, hydrogen, hydrogen, nitrogen, hydrogen, hydrogen, and the total number of electrons here would be 12. So right now I've got 10. So I'm going to put them right here, but carbon's not satisfied, so a double bond has to be put between them. And so now when I look at this, carbon should have 4 valence electrons, and it does have 4 valence electrons assigned to it because there's 1 here, 1 here, 1 here, and 1 here. Remember, half of the bond because they're sharing those electrons. So one gets assigned to one of the atoms, the other one gets assigned to the other atom. And then nitrogen, 1, 2, 3, 4, should have 5, but it has 4, and so that's +1. And so that's where that +1 charge is. The sum of all the formal charges should give you the charge on the atom. All right, and then the last one I'm going to do is CH3COO negative, or acetate. So we've got carbon, hydrogen, 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 and then we've got carbon, oxygen, oxygen. So right now that's 2, 4, 6, 8, 10, 12 electrons, and this molecule would have 24 valence electrons total. And I've got 2, 4, 6, 8, 10, 12. So I need to put out 12 more. So there's 6 and another 6. All right, so this carbon right here needs another pair of electrons because its octet is not satisfied. So I'm just going to take 2 of those and put them down here. Now this has resonance. And if we look at formal charge, this would be 4 minus 4, which is 0. This carbon would 4 minus 4, which is 0. This oxygen right here on the top would have 6 minus 6, which is 0. But this oxygen on the bottom would be -1 because it should have 6 valence electrons. It has 7 assigned to it. Same thing with this one. It should be -1. And so that follows, that is allowed in the resonance structure. And so right here, these bonds would be the same length, and they'd be half single bond and half double bond. We want the structure that minimizes the formal charge. And if formal charge does need to be used, it will be on the most electronegative element. So I'm going to assign the formal charges to these atoms and see which one minimizes the formal charge. And if we do have to have a formal charge on something, it should be on the most electronegative element. All right, so in the first atom, the sulfur should have 6 valence electrons, and it's got 2, 4, and then half of both of those bonds, so that's 6. And so that sulfur is 0. Carbon should have 4 valence electrons by itself, and it's got 2 assigned there and 2 assigned there. And so that's going to be 0. And then the nitrogen should have 5 valence electrons. And here it has 2 in the bond, 2 here and 2 here, so that's 6. All right, sulfur should have 6, and it's got 5, so that's +1. Carbon should have 4, and it's got 4, so that's 0. Nitrogen should have 5, but it's got 7, right? 2, 4, 6, and then 1 from the bond, so that's 7. So that's -2. It still adds up to -1 overall, and so that's how you know you're doing the formal charge right. Okay, and so 6 for sulfur, and we've got 1, 3, 5, 7, so that's a -1. Carbon has 4, and it's assigned 4, so that's 0. And then nitrogen has 5, and it's assigned 3 here and 2 there, and so that's 5, and so that's 0. So which one of these would be the best? It would be the first one, because it minimizes formal charge. And the formal charge that it does have is on the nitrogen. And nitrogen is the most electronegative out of these. And so because of that, it would hold the negative charge before anything else would. And so that would be the most likely structure. Okay, so what is the most likely structure of COCl2? So I drew a couple of different structures on here, and I could keep going. I could make more of these. I could exceed the octet rule with chlorine and just keep making different possibilities. And that's why when I first started teaching this, I said to put the first one in the middle, because it's probably the most likely case. Will it always work? No. This one, it didn't work. So sometimes it would benefit you to draw it 18 different ways and figure out which one is the best. You'll never have to do it in the AP test because there's not enough time for that, obviously, and they know it. But I just wanted to show you, and I'm not going to go through and show you how to calculate each one of these, but I am going to show you what the charge is on them. So this oxygen would have a formal charge of 0, this carbon would be 0, this chlorine would be 0, and this chlorine would be 0. And so that's probably the best structure because you can't minimize the formal charge more than having all of them being zeros. All right, here this would be -1, this would be +1, this would be 0, and then carbon would be plus, and carbon would be 0. Here we've got 0 for that oxygen, 0 for that chlorine, -3 for that carbon, and then chlorine would have a +3. So you can see none of these are minimizing the formal charge as well as the first one. And so that proves that that is the case. All right. I'm not going to assign any more to this. I just wanted to show you all the different variations that you could make, and none of them make it to where all the formal charges are 0 except for the first one.